Well, hello everyone. I am Beth Kemani, the AI ML track lead at Google Developer Group's Chuka University. And today we're going to talk about the art of feature engineering. And so we often hear that data science is 80% data, and that is data preparation and 20% modeling. Yet we go into conferences and we spend 99% of our time talking about the 20%, that is the algorithms. So today we're going to change that and we are going to talk about the 80%, and we are also going to talk about, and that is what we call feature engineering. So in machine learning, our in machine learning our model in a machine learning model, like a world class chef, even the best chef in the world can't make like a 5-star meal out of rotten ingredients. So feature engineering is the process of selecting, cleaning, and transforming our ingredients so that our model can actually extract a signal from the noise. So if our data is messy, our model isn't learning, and it's just memorizing garbage. So let's delve in. So uh, we're going to talk about the pillar, and that is handling missing values. And first thing you'll encounter in real world data set as a whole is an NaN, or a null. So in a school, they give us perfect CSVs, right? But in real world, we have sensor fails and users skip questions, and the database becomes corrupt. So before you write a single line of code, you have to ask, why is it missing? And if it's missing completely at random, that is the MACR, like a random glitch, we can usually just fill it with a mean or median. So but what if like it's missing not at random? So that is the MNAR. So imagine a survey about mental health, right? And people with high anxiety might be less likely to answer a question about stress levels. So if you feel that silence with the average stress levels of everyone else, you have just deleted the most important signal in your data. So, and in those cases, we often create missing indicators. So, um, so we usually create missing indicators, and a new column that says one if the value is missing, and a zero. Okay, one if the value is missing, and zero if it isn't. So sometimes the absence of data is the data. So yeah, so as you can see in slide 5, as you can see here, um, we will use a simple implement imputer. My professional, we will use a simple imputer, and my professional advice so is always default to median. So the mean is easily bullied by outliers, and if you have one billionaire in a so if you have 1 billionaire in a in a room of teachers, the mean income suggests that everyone is a millionaire, right? And the median stays grounded. So yeah, we shall write this code, so don't you worry. But we have to move to the categorical encoding first so that we can go into hands-on. So uh, now we move to the language barrier. So computers are essentially great calculators, right? They love numbers, and they're confused by New York and they're confused by say New York or Paris. So we have two paths here. So and we have one is one hot encoding. I think you're familiar to that because it creates a new column for every category, and it's the fair way to encode. It tells the model that Paris is not greater than London, and they're just different. But we do have a danger zone, and that is the trap. It is the curse of dimensionality. And if you want to encode 500 different zip codes, you just added 500 columns to your spreadsheet, and your data becomes sparse. So imagine you're trying to find a needle in a haystack, right? Difficult. But every time you add a column, the haystack gets 10 times bigger. So yeah, that's the mess. So we also do have the ordinal data. So and the ordinal data is where we add we are and the ordinal data is where order matters, like small, medium, and large. So we use label encoding. So um, yeah, so we use label encoding, and and we assign them 1, 2, and 3, and this preserves the mathematical relationship. So if you use one hot encoding in an on educational level, you're throwing away the information that a PhD is more education than a high school diploma. So do not throw away your domain knowledge. Great. So uh, Um, another thing in feature engineering is scaling and normalization. So this one, perhaps it is perhaps the most overlooked step, because imagine you're predicting health outcomes, right? And you have a column of age, and the age runs from 0 to 100, and you have another column of annual income, and the annual income varies from $0 to $1 million. So many algorithms like KNN or SVM, that is standard vector machine, or even neural networks calculate the distance between the data points. So if you scale your data, the model will look at it will look at the say $110,000. We look at say $10,000 difference in income, and a year difference in age. So and it will conclude that income is 10,000 dollars times or more important. So it's a mathematical hallucination, right? So yeah, and then in terms of normalization, so in terms of normalization, it can also be called min max scaling. And what I mean by this is um, normalization squashes everything between 0 and 1, and we use this you use this when you need a hard boundary, like say in image processing, and standardization, which is also the z-score. It just centers your data around 0 with a standard deviation of 1. Okay, we will understand all this when we get to hands-on, and it is and normalization and standardization are more robust to outliers. And if a data point is like 3.0 after standardization, you know it is an extreme value. So it is an extreme value, that is 3 standard deviations from the norm. So yeah, I think we shall. This is what I was talking about in normalization. So so if you look at the code, if you look at the code, you're able to notice that we scale after we handle missing values. So order of operation matters in feature engineering just as much as it does in algebra. Okay, so yeah, give me 1 second. So yeah, in conclusion, I do have a golden rule, and we have actually covered a lot. But if you remember one thing today, let it be this. Data leakage is the silent killer of models, and never ever calculate your scaling parameters like the mean or the max using the entire data set. So you must split your data into training and testing sets first, and then you fit your scalar on the training data only, and then you transform the test data using those same parameters. And if you use the test set mean to scale your training data, your model has already peaked at the future. So it will look amazing in your lab. So, and if it will fail, and it will also fail miserably the moment you put it in front of, say, real consumers. So feature engineering is where you turn a library of raw facts into a story the machine can read, and this is why you respect data and understand the why behind the numbers, and your models will reward you. So I think we should just delve into the hands-on, but that is basically the nuts and bolts of feature engineering. So yeah, let's move into the nuts and bolts. So um, we shall start by handling data. So just give me 1 second. So yeah, first we shall start by importing the relevant libraries. So we're going to import pandas as PD, and then from sklearn dot impute, we're going to import simple imputer. So let's just do that. And then we shall try to sample data. So what we're doing here is actually sampling data. Sorry. Um, so we should give it the variable. We should give our variable name as df, and then we just say pd dot data frame. We're going to use the same age. Sorry. Then we just give it a list of, just say 25, then 30. Then you can read a CSV file or an Excel file. I just want to make things easier. And 35. Yeah, so there it is. So let's run that. So we shall do the mean imputation. So and in the mean imputation, this is where we like get the imputer. We create a variable, name it imputer, and then we do a simple imputer, and then we try to fit transform. So yeah. And then we shall do a df of age. So we should do, yeah, an imputer transform, and then df age. Yeah, so let's see how that goes. Great. So we should try to drop a few rows. So dropping rows. Once again, you can use your own data set. So you're not confined to using what I'm using. So you can just load your own. So yeah, that is it basically. So we have handled missing data. So if we read there, we actually have the 25, the 30, and the 35. So yeah, that is how it is. So we are going to move into one hot encoding, and this is where we let's see if we can use like a more concrete uh, data set. I think I have one. Oh, no. Yeah, I think I just have to paste this. Just give me 1 second. So I think we just create a new one here so that it becomes easier because it's in the same so yeah, we'll just do everything we have done. So I shall debug. So yeah, so we shall check on so I think we should use house price index. Yeah, just copy that and just paste it here. Great. So So if we run this, so we've just dropped the rows. So yeah, so using pandas, we shall try to do one hot encoding. So hashtag one hot. Yeah, so we shall do a pd data frame. Yeah, so dear, so and we shall take a few columns from here. So we can choose to take, say, stock price index. No, let's just add our own, which is say city, and then okay, and then we just put a list of say New York, or say London, and say Paris. Right, so let's see how it turns out. So we shall do encoded. Let me just copy this. So sorry. And our columns, we shall use so I just have another screen here, so that's why I keep checking if I'm doing the right thing. So let's use population. Let's copy. Yeah, so if we try Yeah, Python is very case sensitive. So you can see our original looked like this. So when we did a one hot encoding, when you try to like do an encoded DF, we have house price index, stock price index, consumer price index, employer rate, real GDP, and now we have a duplicate of we have dummies of population. So we have population these and these. So the list is endless. It goes on and on and on. So that is what that is hot encoding for you. So we should try to use scikit-learn to like do do like a one hot encoding. So from sklearn dot preprocessing, we are going to import one hot encoder. Sorry for the spacing. One hot encoder. So, and we thought we are actually going to like do an encoder. Yeah, which is just equated to one hot encoder. And then we just say sparse, which will be equal to false. Yeah, so we do that, and we do an encoded array, which is encoder say dot fit transform. So we're trying to compare the normal way, the one hot encoder way, and the sorry, let me just connect to Wi-Fi. And also the one hot encoder, and we shall also do one on label encoding. So yeah, you just want to see how they vary each from each. So dear just say, I think we should use the column population again. Population. So if we run this, spelling. So so yeah, that is why you like get to see what has happened to population. But if we use a single array, a single column, say for example consumer price index. So let's move this, and then just if we try to do like the mortgage rate, you will see a difference. So So give me a second, I'll get back to that. So yeah, let's get back to that. So sorry. So I think we should just go back to default. Should use population. Yeah, so let's rerun that and move on. So yeah, basically that's it. You're supposed to see this. But if we try to use the, so this is the one hot encoder thing. So enter. So if we do the label encoder, let me just slide into it. We're going to do the same. So we're just going to change a few things. So instead of one hot encoder, we should do a label encoder. So label encoder, and we shall also do a label encoder underneath. So just give me 1 second. So we shall try to do one. So let's put a data frame. So pd data frame, and then we just give it a variable size. Start with capital letter size, and then we just put that in a list. So we put a list of, say, S. So we said small, medium, large. I hope you remember that, right? So this is what you're trying to do. M, large, and say we have a repetition of medium. Okay, so if we do if we give the variable label encoder the aspect label encoder, and then so we assign label encoder, and then we try to see the outcome. So so we say df, so we say size encoded. My main screen is there, so that's why I keep size encoded. And then we just say le, so label encoder dot our cliche line fit and fit transform. I just dear, and then I just say size. So if we do run this, enter. So if we do run, you can actually see our size encoded, and we can see that it ran from column 1, our size was 2, and remember, as I said, label encoder or ordinal encoder, however you choose to name it, it just assigns each category an integer, so it can be 1, 2, or 3 for like the best ordinal data. So yeah, that is it in hands-on. So where we have S will be the small, and then S, which is the small one, is indicated by O, and then we have M, which is indicated by 1, and then we have large. So please note that it may vary by alpha order. So yeah, so that is it. So if the last thing we should do is scaling. So we shall try to do scaling, and yeah, we shall try to do scaling, and then we shall finish from there. So just so just, and then I'll change here to we shall try to import standard scalar. And we shall also do the min max scalar. Min max scalar. There. So if we give it like some dummy data, so let's run this first to see if we have any errors. So no. So if we give it some data, say for example it's an array, so 100 comma and 0.001, and comma, we just give it another array of 8, and say 0.05, and then comma, we just give it the last one, so 50 and 0.005, and then we try to do the standardization. So let's run this and then do standardization. Yeah, so standardization. So if we try to do a standardization, we shall do a scalar standard deviation. So shall I use the standard scalar? Which we should just equate to, sorry, we need an R here. And then we just do standard data, and then it will be scalar standard say dot fit our cliche line fit transformer. Transform, sorry, just transform, then data. So if we do run this, we do run the great. So you actually get to see an array running from 0.258 to the list being 0.078. So yeah, if we do a min-max scaling, I will do a min-max scaling. We shall actually do a scalar min-max. Limit scalar min-max, and we just equate that to the min-max scalar. So just that, and then we do a min-max data. Sorry, just do a min-max data, and we just equate that to our cliche line, which is Control C, just Control V. So I think we shall change a few here. So it shall be shall do a min-max fit transform data. So if we do mm data, we just get to see that I commented this line. Great. So there it is. So that is basically it. That's the nuts and bolts of feature engineering. So we just did a little bit. So you go do research on your own, add more on the content we have. So yeah, so I'll just talk a little on the problem and also when to use what to use, when to use what. So if you're like missing if you're missing at random, the technique you should use is the mean-median imputation. If you're trying to do nominal categorization, you should use one-hot encoding. If you're trying to do ordinal categorization, you should do label encoding. Then that is why label encoding is also known as ordinal encoding. And if you're trying to check the outliers present just to standardization, and we're doing a bit of deep learning and you're dealing with neural networks, just use the min-max or the normalization. Yeah, so common pitfalls of feature engineering, we do have data leakage. So this is where we have scaling and imputing using the test set. I think I talked about that. So always fit on the train and then transform on test. And then we also do have the dummy variable trap where we have a multicollinearity of one hot encoding where we are dropping one column actually helps, and also when you're ignoring outliers. So scaling can be skewed by extreme values. So yeah. So in summary, just clean your data first, that is handle missing values, and then convert test to numbers, that is what we do call encoding, and then put everything in the same scale, and that is what we call scaling. So thank you very much, and in our next topic, we shall be handling we shall actually delve deeper into neural networks. So this is where we shall do an introduction into deep learning. So yeah, great learning.